first one is going to be by two speakers, actually. And they come from Prowler.io in Cambridge. And ST John is going to start, and then Mark van der Beek is going to continue, and they're going to be talking about invariances in Gaussian processes. So thank you, guys.
Yeah. Hello, everyone. Thanks for being here. I'll be talking about strict invariances in Gaussian processes, and begin by explaining what are invariances, what do we mean by that, give a bunch of examples of invariances to give you better kind of intuitive understanding. Then discuss, okay, so what are they good for? Why do we want to use them? And following that, okay, we want to use them, but how do we actually do that when we want to model functions with Gaussian processes? I'll give some real-world applications of where putting invariances into a Gaussian process model is crucial to actually get it to work at all. And at the end, leading towards Mark's half of the talk, discuss how can we tell whether putting an invariance into our model is a good thing or not. So first, what are invariances? Apologies for the aspect ratio. For some reason now my screen is square and this one is tilted, but you'll have to make do. So invariances are when a function of a point does not change its value under transformation from a point x to t of x, where t is some arbitrary transformation. So if the function value at x is the same as the function value at the transformed version of x, then we say the function is invariant under this transformation. And important point is this has to hold for all points in the domain of your function, and for all transformations under which you want to be invariant. And these invariances, they can be discrete or continuous. So I'll start with discrete ones because I think they're a bit easier to just get an intuitive understanding of. And there's 4 ones that I'll go through: translation, invariance under translations, rotations, reflection, and permutation. So first, invariance under discrete translation. So discrete translation symmetry is we take any point x and we shift it by some fixed amount, they're called d in this example. And our function is invariant if f of x is the same as f of x plus d. But you can also just move the d on the other side, so it has to be the same as f of x minus d, and you can do it multiple times. So has to hold for all integer n. And that's just a periodic function. So if you move by a period in any direction, then you just get the same function value back. So those of you who went to the summer school as well, you probably encountered the periodic kernel in some of the tutorials. And this is about kind of like how can we generalize this to more invariances other than just, okay, I move like by a month in my time series. So another example of discrete translation invariance is if we think of something like crystal. So this is a pictorial representation of a sodium chloride salt crystal. But a key thing to get across here is it's not about the symmetry of the object. It's about functions that are invariant under symmetry operations. So what do I mean by that? So for example, we can think of what's the electron density in this crystal as a function of the coordinates. So x and y. I'll forget about z just because it makes it too complicated. So I've added some coordinates on x and y, 1, 2, 3, 4. And what we mean is that the density at the point 2 and 3 is the same as the density at the point 3 and 4. So for the function, those 2 points look different because one says 2 and 3, the other one says 3 and 4. But we know, because of the crystal symmetry, the function has to have the same value. So we want this function to be translation invariant under shifts by integer multiples of the unit cell. Similarly to translations, we can also have rotational invariance. So this is a snowflake. Up here in Sheffield, you're probably familiar with those. In Cambridge, not so much. So here, for example, you could think of the function that models the density of water molecules as a function of your xy coordinates in the plane. And then because of the six-fold rotational symmetry, if you just know what the density looks like in this sixth of your entire space, you already can fill in the blanks everywhere else. So you don't need to observe the entire plane to know what the snowflake looks like. So you can extrapolate to the entire image from just observing a sixth of it. Next example is reflections. So here you could think about, for example, measuring the solar altitude, how high is the sun above the horizon, as a function of its azimuth. So where is it along the horizon in east-west direction, or as a function of time, like as the sun progresses throughout the day. And you might say, okay, well, obviously it's going to be symmetric, right? And that's basically why we are talking about this, because it's about how can we make use of these things that are kind of obvious to us. If you just use the plain GP and you only train it up to the middle of the day, it will have no idea whatsoever what's going to happen in the second half of the day. Whereas if we put in the reflection symmetry along the midday axis, then once we've observed up to noon, we can already tell exactly what the sun solar altitude is going to be for the rest of the day. Slightly less intuitive maybe at first, but also very important in practical real life applications, is the invariance under permutations. So that's a bunch of coins. You could think about, okay, which quantities of money could I give exact change over the coins I have in my pocket? And so you could think about, okay, first I pick a pound coin out of my pocket, then a 2-pound coin, and then a bunch of pennies. Or you could pick them out in a different order, right? It doesn't matter because about the set of things. But if you think of a function doesn't really take sets of inputs, it takes lists of inputs. So for the function, the order matters. Like 100, 200, 111 is going to be a different input point from 1, 200, 101. But we know that they should have the same function value. So we can impose invariance under permutations. And we actually, like, more practical example maybe is modeling energy of molecules. So we could think of the function that describes the energy of the shape of a water molecule. And so we'll pass in the coordinates of the 3 atoms. But because atoms of the same type are fundamentally indistinguishable from each other, if we pass in the first hydrogen atom, then the oxygen atom, then the second hydrogen atom, it must have the same function value as if we swap the coordinates of the 2 hydrogen atoms. Right, so that was a bunch of examples of invariances under discrete transformations, discrete symmetries. Also works for continuous transformations. So if we think back to the translation example, if we don't just enforce that the function value is the same under integer multiples of the shift vector, but any multiple of the shift vector, that basically means the function has to be constant along this axis. And that may be very useful if you know it obeys this invariance, then you actually reduce the effective dimensionality of the space in which you have to learn a function, and the less dimensions, the easier to learn. Similarly, for rotational symmetry, if you know your function is invariant under rotations of the inputs, then again that reduces the effective dimensionality in which we then have to infer how the function behaves. Another type of kind of translation invariance is if you do image classification and we want to look at the function that returns as the class label given the image pixel matrix. It should give us the same label regardless of whether the cat is in the top of the picture or in the bottom or whether it's rotated by a bit. So these are kind of continuous translation rotation symmetries as well. And for example, if you want to recognize digits in randomly scanned pieces of paper, then it's going to be helpful if you know, okay, it's going to be an 8 regardless which way around it is. And same applies also for the similar example of molecules. I just put a different one on here, but basically the function that gives us the energy of this molecule, the internal energy of this molecule should be the same regardless of whether it's this way oriented or this way or whether it's over here. So the energy should be the same for each transformation of the coordinate system. Now, these were all strict invariances, and to kind of point forwards towards Mark's half of the talk, I just wanted to point out that in real life, often we have something that's approximately invariant. So the first snowflake you saw was actually generated by a computer, so it was perfectly symmetric. If you look at real-life snowflakes, then they're mostly six-fold symmetric, but if you look very closely, if you actually want to figure out the density of water molecules up to each individual atom, you will have to look everywhere because they're not 100% invariant. But knowing a sixth of the snowflake does give you a very good idea of most of the location of the water. And likewise, if you want to classify digits, if you're completely rotationally invariant, it might be hard to distinguish between 6s and 9s. So I already mentioned some reasons for why we want to use invariances, but just to summarize, they basically allow us to incorporate prior knowledge about our system. So physical symmetries that we know must be obeyed by what we're trying to model. So that allows us to make sure that our model is kind of consistent with physics. So if a physical energy is symmetric between swaps of two molecules, would be a bad model if in our model it's not the same thing. This also helps generalization. So basically, if our data obeys some symmetry invariance, then we need less training points to get better accuracy. Any questions on what invariances are and why we care about them? No? All right. So how do we actually incorporate them? Sorry, forgot about that. So just a toy example on permutation symmetry. So this is a function of two inputs, x1 and x2. And I've picked a toy function that's symmetric under swapping x1 with x2. So it's symmetric across the diagonal. And I built two GP models. One knows about the invariance, the other one doesn't. And you can already see the fit of the invariant one looks quite a bit better. But on the next slide, I'll show you what this looks like over the kind of course of training. So if you add one training point after the next, how do these two models infer the function, and what's their kind of test set error based on the root mean squared error of a bunch of test points. So you can see, even though most of the training points are in the top left half of the plane, the invariant GP already generalizes to the other half because it has the invariance in it, whereas the regular GP on the bottom right needs to first get the observations on the other half before it can predict well on that side. All right, so now that we've hopefully motivated why we want to put invariances into GPs, yeah? Yeah. So the question was, why don't we just duplicate the points? Yeah, and like add all the mirror points in this example. And that's called data augmentation, and that's what people do in neural networks a lot, because there it's much harder to think about how do you put an invariance into your function approximator. If you only care about the mean function, then you're right, then that basically gives you the same answer. But it doesn't give you the right variance, because you've kind of, the model thinks there's more data points than there actually are. And also, it's, especially in GPs that scale cubically with the number of data points, if you double the number of data points, you have to pay 8 times as much. Whereas if you put the invariance in, it's only twice as much. Another question?
Yeah, a kind of converse question about why don't you just reduce the dimensionality before you go in there? So if you know it's rotation invariant, just make sure that you're in a deterministic function mapping.
Yeah, that's one of the ways I'm going to present on the next slide. Yeah. Okay, so yeah, data augmentation is something you can do, but yeah, it's kind of like doesn't fit well into a Bayesian framework, whereas this does, as you'll find out later. So yeah, how do we construct the invariances? And you just suggested the first way, which is you figure out an appropriate mapping into an invariant space. But then so I'm going to present that on the next slide, and then after that there's going to be a somewhat more general way of constructing invariant GPs using sums, and I'll get to that in a bit. But yeah, first, if you have a mirror symmetric function, you could just map x1 and x2 to 2 different variables that allow you to only get back to x1 and x2 up to a permutation. So for example, you could take x1 plus x2 and then the norm of x1 minus x2, or you could take the maximum and the minimum, or for more points you could sort them. That's all valid ways of doing this, and there's no unique mapping necessarily. There's lots of mappings you could use to make something invariant. And then we construct an invariant function f using a non-invariant regular function g of the function mapping. So we just say f of x is g of our mapping phi of x. And then the kernel on f is induced by the kernel that we put on g, because we just have to map our 2 arguments to the kernel through the transformation. But it's not always easy to find an appropriate mapping for an invariant, for an arbitrary invariance. So what we can also do is we just do it with a sum. So in this specific example, we can construct an invariant f by taking a non-invariant function g and just taking g of x1, x2 plus g of x2, x1. And then if we swap x1 and x2, because the sum is commutative, then the function value has to be the same, because it's just the same sum. The kernel derivation is a little bit more involved, but it's actually quite straightforward. So the kernel on f is basically the covariance of f at the point x with f at the point x prime. And assuming a 0 mean, just to make the derivation simpler, that's the same as the expectation of f of x times f of x prime. And then we can just put in our definition of f as a sum of 2 evaluations of g. And the expectation commutes with the linear operation. So the expectation of the sum is just the sum of the expectations. And each expectation term in the sum is basically the kernel in G. I hope that makes sense to everyone. If not, okay, white nodding, that's good. So then you end up with the kernel on F being a sum over 4 evaluations of the kernel on G, with all combinations of permutations. So I'm just highlighted that one bit just because there was too much other maths on the slide. But basically, it's a sum over 4 terms. And both of these constructions allow us to now get a GP with an invariant prior, invariant kernel. And you can see 3 separate samples in the columns. The top row is just a regular GP with a squared exponential kernel. You've probably seen lots of those before. And the second row is the mapping symmetrization, so mapping x1 and x2 into different variables in which it's invariant under the permutation. And the third row is the sum symmetrization, where you sum the d's of the different permutations. So how can we make this more general and apply to other invariances? Right, so at this point, just a brief reminder, but a bit more of the maths underlying what's going on here. So transformations can be composed because the invariance holds for any point x. If it holds at x, then f of x is f of t of x. But then we can also just apply another transformation on top of that. So f of t of x has to be the same as f of t prime of t of x, if our function is invariant also under transformation t prime. And therefore, it has to be invariant under composition of transformations. And that means basically that gives the invariances a group structure. So all of the set of all compositions of the transformations that you want to be invariant under, that forms a group, and that corresponds to the symmetry group in your problem. So this now allows us to think of the concept of an orbit. Orbit is a function of a point, and it's the set of all points that are basically equivalent to this point under our invariances. So it's the set of all points that you can reach from the point whose orbit you want to calculate by repeated application of all the transformations under which you want to be invariant. So the set of all the transformations possible applied to your point. And concrete example that we just had, under this permutation of x1 and x2, if I apply it twice, it's the identity transformation. So our set of all transformations is the identity and the permutation. So who can think of what the orbit looks like? Anyone? Yeah? Go for it.
2 points reflected across the
Yeah.
xy.
Yeah, so the orbit of x1 and x2, the same as the orbit of x2 and x1, which is the set of both of them. So on the next slide, you see that illustrated. So in this case, the size of the orbit is always 2. And so if you pick this point, then the orbit contains the point itself and its mirror image. Also works for other transformations. So if we think back to the 6-fold symmetry I talked about earlier, now our orbit has size 6. And if we start out with this point, again, the orbit contains the point itself and the 5 other points that you reach by rotating by 60 degrees. And you might notice this doesn't actually look like a snowflake. That's because snowflakes have more symmetry than just 6-fold rotation symmetry. They're also mirror invariant. So it's actually the combination of the last one and this one. And we can just combine them. Then the orbit size is now 12. And it actually looks quite a bit like a snowflake. But this is just a draw from an invariant GP with zero mean function. All right, so also extends to continuous symmetries. Now the orbit is an uncountably infinite set of points that all have the same radial distance. Or if you think about discrete translation symmetry, the orbit is also infinite. In this case, countably infinite. So if we start from a point here, then the orbit contains all the points that are an integer multiple of periods away. So going back to the sum, we've now defined what an orbit is. We get an orbit based on all the, of a point based on all the transformations. Whoops. And for the toy example of 2D permutation symmetry, we can just rewrite that as a sum over the orbit. And this is now a generally applicable thing. Why is this function invariant under our transformations? Because the function value at x is a sum over all points in the orbit of x. But all points that are invariant under which all points at which the function value should be the same as at x will have the same orbit, because it's kind of this closed set of all points that you can reach by applying transformations. So they will have the same sum, because the orbit of x is the same as the orbit of t of x, and therefore the function value is going to be the same. Now, question?
Maybe I'm jumping the gun here, but if your orbit is uncountably infinite,
then obviously you run into practical difficulties.
It's an integral.
yeah,
But it turns into an integral, and formally I think it's still right. You won't be able to evaluate like this, but Mark's going to talk about how do we deal with that in practice in the second half. If it is a finite set, then we can construct a kernel on F as before, just basically expanding the double sum, and again making use of the definition of the kernel function. So it's now our double sum over orbits of the 2 points of the kernel on G that induces our kernel on the invariant functions. So I've talked a lot about strict invariances. Now to an application that I worked on during my PhD, where we actually made use of a number of these things, and that's molecular modeling. So it's about, if you're interested in the dynamic behavior of a set of atoms or molecules, you want to understand how does my system kind of evolve in time. And to do that, we basically just calculate the forces that apply on all of the atoms and move them around a bit, and then do the same thing again. And to find the forces, we need the gradients of what's called the potential energy surface. It just defines the total energy of our system of atoms and molecules as a function of all the coordinates. And we use GPs to model that, and they have the nice advantage that we can analytically compute the correct gradients. We can predict not just the function value, but also the function value and its derivatives. So that's quite neat, because it gives us consistent forces without having to do any extra work. The only problem is this is a very high dimensional function of 3 times n coordinates if you have n atoms. And n might be 100 or 1,000, so this is going to be a very high dimensional space. And you can't plot it, so I've just picked some random potential energy surface kind of a 2-dimensional subspace of the full potential energy surface, just to kind of give you an idea of molecules kind of move around on the surface, and that tells us about stable equilibria and transition states and things like that. So what do we do to actually turn this into a tractable problem where we can actually apply GPs? The first thing is not so much invariances, but kind of applying our physical knowledge. So that's the many-body expansion. I'll get to that on the next slide. And then a lot of it is actually putting in all the physical invariances that we know our system has to be obeying. So the first thing is we have a function of 3n arguments, and we write this as a sum over single body terms, 2-body terms, and 3-body terms. In principle, you could expand this to functions of an increasingly larger number of combinations of atoms. But generally, higher order contributions are going to be much, much smaller in scale. So it's a decent approximation to just forget those and just say, OK, we've got contributions due to things by themselves, things interacting with other things. And then the 3-body term is kind of like you have an interaction between these 2 objects. How does the third object change how they interact with each other? Slight complication, actually, it's not just atoms. So then the 3-body term would just be a function of 3 atoms. But if you do molecular modeling, you have to kind of take into account molecules as a whole. It doesn't really make sense to split them up. So the single body term is already going to be a function of as many atoms as you have in one molecule. So for example, if you think of water molecules, then the 2-body term already is a function of the 3 times 6 coordinates, 18 coordinates of the atoms in here. And we might actually end up with even that's basically the smallest molecule there. So it's still fairly high dimensional functions, but now it's on the order of less than 100 maybe instead of thousands. So we want to make use of the fact that the energy, the interaction energy between these two water molecules should be the same, whether you find them like this in your system or like that or over here. It should all be the same, right? So it should be invariant under translation and rotation. And what we did here is basically just use the first approach of mapping it into an appropriate space that's invariant. And specifically, we just used the set of all interatomic distances, because distances are invariant under translations and rotations. But a lot of these distances are actually kind of equivalent to each other, because you could just swap the order of atoms in your system, and then you would get different distances, but they should give you the same energy and forces because they represent the same physical system, even though the coordinates in the computer are different. And for that, we actually used the sum construction over all kind of valid permutations of these atoms that leave the system invariant. Yeah, sum over them. All right. Any questions so far? Otherwise, yes, no? I'll quickly press on for the last point, which is, in that case, we knew we have these physical invariances, they need to be in the system. That may not always be the case. So how can we figure out whether an invariance is useful in modeling a data set or not? And what we are basically suggesting here is do it the same as you would for kernel hyperparameters, where you optimize the marginal likelihood to find out what's the best value for your length scales and variances. And unlike the kind of regular likelihood that's equivalent to the training set error, the marginal likelihood leads to less overfitting, and that's because it's actually related to generalization. So you can think of the marginal likelihood as a measure of how well some part of your training set actually predicts the rest of it, because you can write so the marginal likelihood is the probability of the data with your model parameters integrated out, and you can write that as the probability of the first data point given your hyperparameters times the probability of the second data point, given that you've already taken the first data point into account, and so on as a kind of telescopic product up to the probability of the last data point given all the ones you've seen before. So this kind of tells you how accurately the model generalizes like during the inference, and you can think of it as similar to like leave one out cross-validation, except this construction is differentiable, which is going to be crucial for Mark's talk. And as a final point, this is the same toy example you saw before, and now I've just added both the log marginal likelihood and training and test set root mean squared error. And you can see that because there's some noise on the training observations, the non-invariant model actually has a smaller training set error than the one with invariance put in. But the invariant one that actually corresponds to the ground truth has a significantly better log marginal likelihood, as well as a much better test set root mean squared error, about a factor 2 better. And with that, I'm basically out of time for my half. So I just want to summarize what I've told you about, and then Mark's going to pick up on that. So I've discussed what are invariances, why might they be useful, how do we put them into our GP prior, and showed you that they do exist in real-world problems, and that the marginal likelihood helps in figuring out whether they're the right ones or not. Do you want to swap over, and then we can take questions while you're setting up your laptop?
We'll have some time for questions at the end.
Yeah, there's also that. But if you have any questions on the first half of the talk, now's a good time. No? Great. One question.
So with this, you had this series where you showed that when you have higher combinations of much more like atoms, then this essentially you can cut it off at a certain point because it's less important. But would that be really the case? Like, would that be like when you deal with the chemical molecules and you keep adding like at the leaves of your tree, essentially you would have some atoms which sometimes make a big difference in the
Yeah.
behavior of the
So your question was whether the sum actually terminates,
is it
and
viable to actually
that's why I said you kind of have to think of molecules as a whole. So what I meant is you have the energy of a single molecule, then the kind of interaction energy between two molecules, but two entire molecules, not just like one molecule and 95% of the other
I guess
molecule.
what I'm getting into is, have you actually considered this combinatorial increase in complexity, where you have more and more items you have to
Oh yeah,
around? Have you actually tried
definitely
to
an issue, but we can discuss that
Yeah, for
after
sure,
the
yeah.
talk if you want.
In the
Alright.
meantime, I'm having a few small problems with my
Can we swap my
Oh yeah.
setup. I think I've got it.
You just need this apparently.
Yeah. All right. Yeah, okay, so I'm Mark, and I'll be picking up where T left off. And essentially the problem that I want to discuss today is complementary to what T discussed, where T discussed how to use known invariances to predict, to improve predictions. I'm going to talk about how you can discover invariances that you don't know are in your data set in order to improve predictions. So yeah, just a quick recap of what T spoke about. Essentially, T spoke about how to construct Gaussian processes, which are distributions over functions which are invariant, when they invariances help improve the model's generalization, i.e. when the problem that we're trying to address has similar structure, when the invariance increases the marginal likelihood, and T showed that invariances exist in real-world problems. So I want to go from known invariances to figuring out what invariances exist in a given data set that we don't know very much about. So let's say that we're given a particular data set and we know that there are kind of some invariances in them. How can we exploit them if we don't know which one is in there beforehand? So to illustrate this, I just want to draw a quick example. Imagine that we've got like a classification task where we've got loads of positive examples like this here, and then we've got some negative examples scattered around like this. Now, what should you do if you're asked to predict what's going on here? Well, if you use a standard squared exponential kernel for this particular problem, then because it's far away from all data points, the squared exponential kernel would just predict high uncertainty 50-50, right? Whereas actually what we would want to do is we would want to observe that there's this pattern here, right? There's this pattern that the decision boundary between the two classes is actually rotationally invariant. So if we can figure out that there's a rotational invariance in this problem just from this data set, and there is quite a lot of evidence for that just by that semicircle there, then we would be able to predict much stronger what's happening over here. So that's the aim of what we're trying to achieve. Now, how do we want to do this? Well, as T essentially alluded, we can incorporate invariances into kernels. And so let's say that we've got a whole bunch of kernels with different invariances that are candidate invariances for the problem that we're considering. Then picking the kernel with the right invariance is just a standard problem in Gaussian processes, right? We want to pick the kernel which maximizes the marginal likelihood. Essentially, it's a hyperparameter selection problem where the hyperparameter determines the invariance that is present in the kernel. So if we take a look at the sum construction in particular, we've essentially got the property that the invariance in the kernel is parameterized or determined by this orbit. So if we could just parameterize this orbit, then we could essentially, and in doing so parameterize a whole bunch of invariances, then we could parameterize a whole bunch of kernels that have different invariances in them, and we could learn the parameter of the orbit simply by maximizing the marginal likelihood. So conceptually, I'm thinking about this in exactly the same ways I'm thinking about kernel hyperparameter selection. But the challenge is in parameterizing the kernels with different invariances. So the first major problem that I encountered when I was thinking about this was that parameterizing orbits is actually really hard. And I still don't really know how to do this. And the reason for this is that invariance is actually a really strict criterion, right? Like we're actually asking to create a distribution over functions where the function value is exactly the same if we apply a particular transformation to the input. So this requires us parameterizing this orbit function that has the property that if we give two different inputs which might be far away from each other, that can be transformed into each other by these transformations that we're interested in, then this orbit function needs to return exactly the same set of points. Now this is a super complicated requirement, and I'm not sure how to parameterize a set of functions that would have that property. So in order to still achieve our goal, we're going to relax this requirement a little bit, and we're going to stop thinking about strict invariances and think about something slightly more approximate. So instead of summing over a set of points which has this complex property of being an orbit, I'm proposing let's sum over an arbitrary set of points instead. And to make things a bit more easier for a bunch of reasons, to make it differentiable and all that kind of stuff, let's take the infinite limit. So instead of summing over a set of points, we instead take an integral over a probability distribution. And then we essentially find a very similar kernel to the double sum kernel that we saw earlier. So here we've essentially got a double integral kernel where we integrate over a prior of this g function that we use to construct our f. And we integrate this over these, essentially the density of points that we smear out over. So the nice thing is now is that I do know how to parameterize distributions, although the downside is that I don't know how to compute these integrals. So that's a problem we're going to have to solve later. But at least conceptually, we've now, by parameterizing a rich class of probability distributions, we've now parameterized a rich set of kernels that get summed over certain sets of points. So the first thing we can observe about these kernels is that these kernels include invariances, but they also include a lot more things. And I just wanted to take a minute to think about what else this class of kernels contains other than strict invariances. So in order to do this, I just wanted to, I've got this image which kind of shows the relationship between the invariant function and the non-invariant function that we sum over to construct the invariant function. So here I've got a rotational invariance. This is one of the invariances that T showed earlier. And what I've plotted, essentially, is 2 points that have the same value because they're in the same orbit. And I've plotted the corresponding orbits of those 2 points. And we see that the orbits are shared, and we see that, well, we'll sum over these particular values, and because the orbits are the same, we'll sum over the same function values in G, which means that the function values in F are the same. And then here, essentially, I look at this in slightly more detail. I plot what the function does along the orbit, and here I show where we average. Question?
So the P of XA given X, that distribution,
Mm-hmm.
that's the distribution, so the density over which the orbit lies.
So in this particular case, it's a uniform distribution over the orbit, yeah. It's called the Haar measure.
Okay,
Yeah.
cool. But it's got over the entirety of the space, but it's only got mass on that ring.
Yeah, you can see it in that way. Is there another question?
I understand how you can represent orbits like the invariant.
Mm-hmm.
I don't understand how you can represent a simple orbit like a simple symmetry, which is 2 points.
That would be 2 delta functions. Yeah. Yeah. So this approach is mostly suitable to continuous invariances, and I guess in the limit you can get discrete invariances. Any other questions? Right, okay. So what I want to show in the next slide is what happens when we start taking averages over not the entire orbit, right? So this gives us a bit of an impression of what happens when we sum over more arbitrary sets of points. So in this animation, essentially I start by summing over a single point, and then I grow the orbit slowly to include the entire orbit. And what we'll see here is the resulting function that we get by summing over this partial orbit. So what's interesting is that we see that as the orbit grows, the amount of variation in the function along the orbit actually becomes smaller. And we're actually interpolating between completely non-invariant functions and completely invariant functions. Right? So the two functions start off exactly the same when we start just by summing two initial points. But then as we grow this density to include the entire orbit, we get something that's completely rotationally invariant. So what I'm trying to illustrate with this is that not summing over orbits still gives something that we can interpret, right? Essentially, it gives us a function which isn't exactly invariant to perturbations of the input, but the variation in the function decreases in perturbations of the input. And the perturbations of the input are measured by this distribution that we sum over. Any questions? Right, so to make this a little bit more concrete, I'll introduce the example that I'm interested in. And so essentially what I'm going to talk about in the next part of the talk is turning a normal classification task of MNIST using a squared exponential kernel, which is a very weak kernel, into a much stronger kernel by making it insensitive to perturbations that don't really change the identity of the image, right? So we said earlier that the distribution that we average over kind of determines what perturbations of the input don't change the class label. So here I've given an example of such a distribution, and in the squared images are the input images, and in the rest of the images we see samples of perturbed images, right? And all these perturbed images are slightly modified versions, right? So we see slight rotations, we see skews, we see scale variations, right? That one's a lot smaller than that. And these are all perturbations that we want our classifier to not change the label for. So this is a distribution that represents this insensitivity. And this distribution then defines a kernel. And then what we're going to try and do is we're going to try and parameter or maximize the parameters of this distribution, which determines how much variation is in here and which variations, whether it's only rotations or only skews. We want to maximize those parameters with respect to the marginal likelihood. So that's the goal. Right, is it clear what we're trying to achieve here? So actually doing this is challenging for a whole bunch of problems. So essentially, we've got the kernel, which we can't evaluate because it's got this double integral. We've got the marginal likelihood, which is intractable for large data sets for the usual reasons. I'm sure you've heard about that during the summer school. It's also intractable because we've got non-Gaussian likelihoods. So these are the obstacles that we need to overcome if we actually want to learn these parameters. Now, the standard approach, which is by now standard, but was developed in a large part here in Sheffield, is variational inference for Gaussian processes, right? So this is a very elegant way to deal with this problem of large data sets and non-Gaussian likelihoods. So those two problems are kind of solved. So the problem that we're going to look into is the fact that we still need to evaluate our kernel in order to evaluate all these matrices in the variational approximation. And that's the main problem that we're faced with, right? Because we can't perform this integral analytically. Right. So the first part of the solution comes in the form of interdomain inducing variables. And essentially, in order to figure out what we need to change, we first need to kind of look into more closely where the problem's coming from in the variational approach outlined above. So essentially, earlier we saw that to calculate this predictive mean and predictive variance of the Gaussian of the approximate Gaussian process, we need to compute all these kernel matrices, which depend on these covariances with integrals that we can't compute. Right, so that's the source of the problem in still trying to do the variational approach. And the reason why we need to compute these covariances is because in the variational method, we construct the variational posterior by conditioning on points of the function that we observe. Right, and in our case, that function is the invariant function. Right, so we need to ask for the covariance between our inducing point, which might lie in this space, and our predictions, which require these double integrals. So that particular choice causes us to rely on this double integral kernel. So what's the solution? Well, the solution is essentially that we can, if we realize that we construct our invariant function from this non-invariant function, and that the non-invariant function has a kernel which is really easily computable, we can kind of wonder, well, maybe can we place the inducing points in the non-invariant function? Right? So instead of learning about sparse points in this invariant function, we can say, well, there's a deterministic relationship between this invariant function and the non-invariant function. Why don't we just learn about the non-invariant function instead and let that represent the knowledge that we have about the invariant function? So the nice thing is that if we place the inducing variables in this space of the non-invariant function instead, then we need to compute different covariances between the inducing points themselves and between the inducing points and the points we want to predict. So we can derive those covariances in the usual way by taking expectations over the construction, just like T did in the first part of the talk. And we actually find that it's a single integral for the covariance between the non-invariant function and the invariant function. And there's no integral in the covariance between the inducing points themselves. So what we get is that the covariances, by placing the inducing points in this space, we get that the covariance between the inducing points themselves is just the original covariance which we can easily compute, and the covariance between the inducing points and the observations becomes a single integral. We still can't compute the single integral, but it's less bad than a double integral. But what we can compute is the inducing point matrix itself. So we've made some progress. Right, so how do we deal with the remaining intractable terms? Well, the first thing that we can observe is that if we use a Gaussian likelihood, then our variational bound only depends on the predictive mean, the square of the predictive mean, and the predictive variance. And we can observe that so essentially all we really need in order to evaluate this bound is some kind of unbiased estimate of this predictive mean and this predictive variance, right? Because if we get a noisy unbiased estimate of the objective function that we want to compute, then we can use stochastic gradient descent in order to still optimize it. So if we look at this in a bit more detail, we realize that this covariance between the inducing points and the observations is just a single integral over a particular probability distribution. And the other term, this covariance between predictions themselves, is a double integral over probability distributions. So this lends itself naturally to just getting a Monte Carlo approximation for these two terms by sampling from these distributions, i.e. sampling our augmentation distribution, taking the means, and then plugging that directly back into the form of the marginal likelihood lower bound. So taken together, all of that creates so taken together, these two tricks give us a working method. We've essentially removed the intractability from these covariances between inducing points, and we've got unbiased estimates for these guys. I've skipped over a few details. If you're interested in the details, we constructed some slightly clever estimators which reduce the amount of samples that we need to take. The details of that are in the paper. Right, so just to recap again, what did we do? We parameterized a kind of perturbation process which determined which perturbations of our input we wanted to be insensitive to. We used that perturbation process to define a kernel that was insensitive to these perturbations, which we couldn't compute. Then we approximated the marginal likelihood for the usual reasons using variational inference. But then in order to get around the problem of not being able to compute the kernel, we found out a way on how to use unbiased estimates of the kernel in order to still get an unbiased estimate of the marginal likelihood lower bound. And then using this unbiased estimate of the marginal likelihood lower bound and its gradients, we could then optimize the parameters of this distribution, which determined the insensitivities that we want to use for classification. Any questions? All right. So yeah, just to give some results. Essentially, what we ran 2 experiments with exactly the same model. We tried to do MNIST classification, and we also ran the classifier on a version where all the digits of MNIST were rotated. And essentially what we started with was a non-invariant kernel, which is an RBF, right? And one of these squared exponential RBF kernels, it essentially only uses smoothness to determine what, or kind of Euclidean distance smoothness, to determine what 2 images are kind of similar enough to have the same label. And then what we did is we added, to that squared exponential kernel, we added these insensitivities to perturbations, and the perturbation process was essentially random affine transformations. So we wanted to learn whether it was kind of rotationally invariant, or how rotationally invariant, how scale invariant, how skew invariant, and all that kind of stuff. And these are the parameters we were trying to learn. And what we essentially observed is that this same method would not only improve the classification for MNIST by finding all these kind of perturbations that MNIST digits are insensitive to, but if you ran it on the rotated MNIST dataset, it would learn that it had to be way more rotationally invariant than for the original MNIST dataset. So I think this really illustrates kind of the power of this automatic tuning of hyperparameters, because if you wanted to do this in a deep learning setting, you'd kind of have to do cross-validation over specifically designed neural networks that have particular invariances built into them. But in the kind of the beauty of the Bayesian framework, where you've got this marginal likelihood, you can just set something off with optimization and optimize the marginal likelihood, and it will automatically find the right thing to do. So yeah, with that, I hope that you agree that we can parameterize interesting invariant kernels, and that the marginal likelihood is a good objective function to learn the parameters of these invariant kernels with, and that the fact that we can't compute these invariant kernels, we've got approximations to deal with that as well. And finally, that the incorporation of these invariances improves the generalization capability of our models as well. So yeah, I hope that was interesting for you, and we're here to answer any questions.
There's a question.
Ah, yeah.
So, most of the invariants we're looking at seems to be focusing on some symmetries and rotation stuff. So there might be some invariants you get over domains, which is usually some periodic stuff, right? Where you sort of have domains that repeat themselves in various sorts of shapes and tessellating. Have you done an exploration of that, or so I just think that strikes me as a
So I guess your work used a lot of kind of periodic invariances over discrete invariances over periodicity, right? I guess the invariances that I was looking at to learn in most kind of image classification tasks, you don't really see an awful lot of periodicity. Most of it is finding the right directions, finding these right perturbations in order that your classifier should be insensitive to, right? So yeah, but in principle, the framework applies to pretty much any invariance, right? The difficulty is just how do you parameterize a kernel that contains a particular invariance, and can your gradient optimizer actually get there?
Question over there.
Thank you, very, very nice talk. It's been all 2 talks nearly. So question, so clearly this P of XA term is very important, right? Because
yeah.
Otherwise you can use collapse to, I can use make everything the same, right?
Yeah, if you choose a delta function, you end up with the original kernel,
Yeah,
right?
exactly.
Yeah.
So what is that term actually?
The pxa given x?
Yeah.
So this is the process that perturbs our input, right?
Yeah.
So essentially, if we take a look at this animation, this is essentially the density of pxa given x.
Right.
And it determines the perturbations that we want to become insensitive to, right? So as we, yeah.
Right. So that's how you specify the invariant.
Exactly.
Right. So now then, thinking about like richer classes of these things, like how do I, or you're saying I have multiple of these classes, but I prefer this one to that one. Yeah. How does one actually specify it, or do you compare them under the marginal likelihood?
So we do hyperparameter selection using the marginal likelihood. So I strongly believe that the marginal likelihood is the right metric to compare these different classes on. In terms of, you said something about that hinted towards putting priors on these parameters or something like that.
That's right.
You could totally do that, and I guess if you wanted to do sampling over these hyperparameters, you might have to use some kind of pseudo-marginal approximation, right? That can leverage random or noisy evaluations of your probability ratios.
Because wouldn't it be that if I don't place priors over these things, that I can effectively, and compare it under the marginal likelihood, I can find a transformation that just collapses everything into one point, and it correlates everything with everything, and there's an invariance that just makes everything one point, right?
So that's overfitting, right?
Exactly.
Yeah. So if you make your class of invariances so large that you can pretty much correlate everything with everything, then you run the risk of overfitting in the same way that if you do normal maximum likelihood, then you overfit as well. But so I've actually found it very hard to parameterize very, very rich classes of invariances. So I guess my own inability to parameterize super flexible things has meant that overfitting isn't a problem here. But I do think that the future power of these kind of methods will depend on how rich of classes of invariances you can parameterize.
Any other questions?
You mentioned the paper was.
Oh, the paper is called Learning Invariances Using the Marginal Likelihood. It was published at NeurIPS in 2018, together with Matthias Bauer and James Hensman.
Does no one else have any questions? Then I've got one for you.
Oh, all right.
So you said you can use variational inference to then use any likelihood.
Oh yeah, that's a really good point. So I snuck in a little bit of something sneaky. Essentially, I made an assumption about a Gaussian likelihood, whereas earlier I said that variational inference can be used to not have to deal with Gaussian likelihoods. So the success of this method depends on only linear and quadratic dependence on the predictive mean and predictive covariance of the Gaussian process. But there's this trick called the polygamma trick, which allows you to turn many non-Gaussian likelihoods into variational approximations which only depend on the predictive mean and squared variance. And we actually use that in the paper as well. So yeah, thanks for that question. Other than that, we'll be around to chat to if there's more you want to ask us. But thanks for your attention.
Thanks, and Mark again. So we have another session of coffee.